All right, in this video, we will be going through and looking at the practice exam from our study guide for mini exam 2. Now, this exam practice guide, this is not quite a mock-up of what the exam is going to look like, but it is pretty close. And so what we're going to do is what I would like you to do is if you haven't actually done it yet, stop this video right now and go and just try to do as much of this exam as you can in a 45-minute time window. Just take that 45 minutes, see how far you can get, see how much you know. That'll give you a good idea of how much preparation is necessary and how much you need to do to get ready for the exam itself. So if you haven't done that yet, go ahead, pause the video, stop the video, go take care of that, then come back and see how you did. And if there's stuff that you're just stuck on, I'm going to go through every single question here in detail, show you how I did it, and do all that kind of thing. So starting here with the first question, Chapter 8, we're looking at balancing equations and determining the type of the reaction. And so just as a reminder to ourselves here, I'm going to write over here in a box what the types of reactions are. So we've got combination, we've got decomposition, we've got single replacement, we've got double replacement, and we've got combustion. So those are our possible options for this particular problem here on the right. Let's see what that looks like. So first and foremost, we're going to start with the types of reactions because we can actually identify the type of reaction without actually doing this balancing part here. So things that we want to look for. In combination reactions, we want to look for the merging together of multiple reactants into a single product. And I can see that from this, we have no single products here. So we can right away take combination off of the list. We have no single products here. Now, decomposition reactions are when we have a single reactant that breaks apart into multiple products. None of these have single reactants, so that one can go off the list as well. So all four of these reactions are either single replacement, double replacement, or combustion. Now, of those three, two of them are very, very similar, the replacement reactions. The one that is different is combustion. For combustion, what I need to be looking for are a reaction with oxygen and carbon dioxide and water as products. And if I look at letter D here, I can see in letter D here that we have a reaction with oxygen forming carbon dioxide and water as products. This is a combustion reaction. Now, none of these other ones fit that description. In fact, we can see that all of these involve some kind of switching taking place. I've got the iron and the silver switching places here. I've got aluminum and silver switching places here. I've got silver and sodium switching places here. Those are all hallmarks of replacement reactions. So we're done with combustion. Now it just becomes a matter of which of these are single replacement and which of these are double replacement. And remember the difference. Single replacement reactions, I have one compound on each side of the equation. Double replacement reactions, I have two compounds on each side of the reaction. That's the single and the double part of single and double replacement. So in letter A, I see I have silver nitrate compound, so that's one. Sodium carbonate compound, that's two. Two compounds, we're talking about double replacement. For the aluminum, aluminum's not a compound. Okay, it's an element. Silver oxide is a compound. So I've got silver oxide on the one side, I've got aluminum oxide on the other. One compound per side, single replacement is this one. I've got iron 3 iodide here, silver nitrate here. Both of those are compounds. Two compounds means double replacement. So we can identify replacement reactions based upon that. We can see things switching. But more importantly to us here, we can identify single versus double by looking at how many compounds there are. So we've done the second part, the second task there. Is it okay that we did it out of sequence? Absolutely. Doing this part has nothing to do with balancing these equations. What we find, however, is that balancing equations gets a lot easier if I have replacement reactions compared to any other reaction. So let's go through the balancing process here. Now, for each of these balancing ones, what we're going to need to do is we're going to want to set up some kind of scheme here that allows us to look at each side of the equation and kind of what the key components of it are. So in part A, I've got silver. I've got nitrate ion. I've got sodium. And I have carbonate ion. And remember, the reason that I can keep the nitrates and the carbonate together in this scenario is because they are the same on both sides of the equation. So I've got nitrate here, carbonate there. Just working it out, I have one silver here and two over here. I've got one nitrate here and one over here. I've got two sodiums over here and only one over here. And I've got one carbonate on each side. So my silver is out of balance, my sodium is out of balance. I pick one, it's going to affect the other. So I'll start here with my I'll start here with the sodium. I'm going to need two sodiums. That's going to turn my sodium from 1 to 2, my nitrate from 1 to 2 as well. So sodiums are now balanced. Silver and nitrate are now out of balance. To fix that, I'm going to take a 2 here to silver nitrate. And that's going to put the silver at 2, the nitrate at 2. And I can see that now across the top all the way, everybody's all balanced out. So I'm done here. For the next one, I've got aluminum, I've got silver, and I've got oxygen. So a little bit less complicated of an example. We'll take it. There are 1 aluminum, 2 silvers, and 1 oxygen on this side. There are 2 aluminum, 3 oxygen, and 1 silver on that side. Nothing's balanced right now. So here's where one of my balancing equation tips is going to come in handy. If you're looking at a compound that has multiple subscripts like that does, use that to start the whole process. So I need 2 aluminums. I'm going to put a 2 right there. I need 3 oxygens. I'm going to put a 3 right there. Now I just changed 2 things at once, but let's see what it does for me. That turns that into a 2. 3 times 2 is a 6. 3 times 1 is a 3. Well, in doing those steps, I've balanced the aluminum. I've balanced the oxygen. The only thing I haven't balanced is the silver. To balance the silver, I need a 6 right there. Now turn that into a 6, and now everything's all balanced out. For the third one, I have iron, I have iodine, I have silver, and I have nitrate. So I'm starting with 1 iron, 3 iodine, 1 silver, 1 nitrate. I'm turning in 1 iron, 1 iodine, 1 silver, and 3 nitrate. This is very similar to the first one that we balanced, where we've got different things that are out of balance. And so we're just going to kind of take them in turn. So to balance out the nitrates on the reactant side, I'm going to need 3 silver nitrates. That's going to give me 3 silvers and 3 nitrates. So the nitrates are now balanced. I'm going to need 3 silver iodides to balance that. That's going to give me 3 I's and 3 silvers. Everything's now balanced. For the last one here, we're dealing with a combustion reaction. Combustion reactions are notoriously, well, finicky, fickle, difficult. Because we've got lots of things going on, and sometimes the math doesn't always work out in our favor. But let's get started. So we start with the carbon, the hydrogen, and the oxygen. And for the carbon, I had 4. The hydrogen, I have 10. The oxygen, I have 2. On the other side, I've got 1 carbon, I've got 2 hydrogens, and here's where it can be a little bit tricky. I've got oxygen in multiple places here. I've got to remember that. So 2 here plus 1 there is a total of 3. Now we can use a similar kind of trick that we used up here, since we have multiple subscripts here. So if I do that, that can give me at least a starting point for carbon dioxide and since I have 10 hydrogens, 5 waters, because 5 times 2 will give me the 10 that way. And if I do that, I end up with 4 carbon, I have 10 hydrogen, and I have 8 plus 5, 13 oxygen. This is where things can get a little bit tricky and fuzzy, though, for us. I have 13 on the product side. Oxygen only comes in pairs on the reactant side. What do I do? Well, technically, there are 2 ways to look at this. I could put a fraction in here, 13 over 2. 13 halves times 2 would give me 13. I've balanced the equation technically. However, most folks don't like fractions um, in their equations. So what that means is if I do this, that fraction is going to be there. That's not going to be pretty. Most are not going to accept that as correct. What I need to do then is I need to multiply all that by 2 to get rid of the fraction. And when I do so, it's going to change my numbers. I need 2 of these now. 2 times 4 means I need 8 of these. 2 times 10 means I need 10 of these. So if I come back to the drawing board, this is now 8, this is now 20, this is now 8, this is now 20. My oxygen count is 16 plus 10 for 26. And now I have a number that I can put in here that makes sense. I can put 13 here. 13 times 2 will give me the 26 that I need. Now everything's all balanced out. So combustion reactions can be a little bit tricky when it comes to balancing them and balancing them properly. But if you kind of hold true to some of those kind of guiding principles that we've been talking about and use some of the tricks and places to look for shortcuts inside of the equation, you're going to find that you end up doing okay. Now, the other big concept out of chapter 8 was this, the stoichiometry stuff. And so questions 2, 3, and 4 on this study guide are all about stoichiometry, limiting reactants, and percent yields. So they've given us an equation here, the reaction between nitrogen and hydrogen to make ammonia. The question is, for number 2, if 35.0 grams of nitrogen and 35.0 grams of hydrogen react to form ammonia, what is the limiting reactant? Show your work, use the correct number of significant figures. Now, there are lots of ways to solve this problem, especially if you look in light of what is being asked in question number 3. Question number 3 asks you specifically, what is the mass of ammonia that can be produced from that same amount of nitrogen and hydrogen? So what I would do as a student looking at these 2 questions together is I would say, oh, they're asking about the same thing. Can I do something that would allow me to answer both questions at the same time without having to do a whole bunch of work, or at least limiting some of the work that I do have to do? And so the answer to that question is yes. What we can do is in each case, each scenario, we can set up our mole map where we're going to start with 35.0 grams of nitrogen and 35.0 grams of hydrogen. And we're going to try to figure out how much ammonia each one of them can make. So we're going to do the same stoichiometry process for both of them. So let's start with the 35 grams of ammonia, 35.0 grams of nitrogen. My first step is to turn the grams of nitrogen into moles of nitrogen. For that, it's a molar mass. I need a periodic table. Got mine right here. Molar mass of nitrogen is 14.01. So two of them would be 28.02 grams in a mole. My grams of nitrogen cancel. Now I'm at moles of nitrogen. Second step would be to convert the moles of nitrogen into moles of ammonia. That relationship comes from the balanced chemical equation. I've got 1 nitrogen. I've got 2 ammonia. My moles of nitrogen cancel. I'm now with moles of ammonia. Last step is to take the moles of ammonia and to convert them into grams. Again, molar mass, need a periodic table. Nitrogen is 14.01. Hydrogen is 1.01 times 3, since there are 3 hydrogens, 17.04 grams in a mole. Moles of ammonia cancel. I'm at the end of the stage here where I'm supposed to be. 35 times 2 times 17.04 divided by 28.02 to 3 significant figures, because I'm starting with 3 here and none of these have fewer digits. It's 42.6 grams of ammonia. Now, is that correct for the theoretical yield? We don't know. We won't know until we figure out how much that hydrogen is going to make. So let's calculate that. 35.0 grams of hydrogen. We want to turn the grams of hydrogen into moles. Hydrogen is 1.01 times 2. It's 2.02 grams in 1 mole. My grams of hydrogen cancel. My next step would be to convert the moles of hydrogen into moles of ammonia. Again, the balanced chemical equation is going to pull that for us. 3 hydrogen and 2 ammonia. My moles of hydrogen cancel. Last step is actually the same as this step. 1 mole of ammonia weighs 17.04 grams. My moles of ammonia cancel. 35.0 times 2 times 17.04 divided by 2.02 divided by 3 to 3 significant figures again. We've got 3 here. None of these have fewer. We get 197 grams of ammonia. Now remember, for limiting reactant problems, we want to focus on the reactant that makes less. The reactant that makes less is the nitrogen. So the answer to the question, what is the limiting reactant? We've got an answer. It's nitrogen. And we now have the evidence and the proof to show so. Now, for question number 3, we've already answered this question. What mass of ammonia can be produced from these? Our answer, 42.6 grams. Question asks us to circle our work. Well, it's this work right here that we did above. So before we move on to this last question here, where we talk about the 32 grams of ammonia and figuring out the percent yield, what if, I mentioned there were multiple ways to do this problem. A secondary way to do this problem would have been, instead of using the nitrogen to convert into hydrogen or into ammonia, we could have taken the nitrogen and converted it into hydrogen. That process would have looked something like this: 35 grams of nitrogen. There are 1 mole of nitrogen for 3 moles of hydrogen, and every mole of hydrogen weighs 2.02 grams. So basically, we're just taking the guts here and we're just rearranging them a little bit. The end result, we are solving for hydrogen. 35 times 3 times 2.02 divided by 28.02. To 3 significant figures, we get 7.57 grams of hydrogen. Now, what good would this information be to us? Well, what this information would tell us is all of the nitrogen is gone after 7.57 grams of hydrogen have reacted. Well, do we have 7.57 grams of hydrogen? Yes. In fact, we have quite a bit more. We have 35 grams. So this amount of nitrogen is used up, and we still have 27.43. We've got a good bit of hydrogen left over. That's a case for proving that the hydrogen is excess. And if the hydrogen is excess, then the nitrogen must be the limiting reactant. So that would solve question number 2 up here. And then for question number 3, you would have to do this conversion to ammonia with the nitrogen anyway. So both are good approaches. Both will get you to the same place. It's just a matter of thinking which one kind of makes the most sense to you. I kind of prefer this first method here, where I kind of look ahead a little bit and do both calculations at the same time and compare. But you're really not saving that much work or losing that much extra going the other way. So just as a kind of an aside there, you would be well within the realm of logic if you did that kind of conversion to figure out the limiting reactant first. Just have to remember that to find the theoretical yield, you have to start with the limiting reactant. So you have to start with the nitrogen. If you do all of that and determine that nitrogen is the limiting reactant, and then do the hydrogen calculation and convert that to the product, you're getting the wrong theoretical yield. So the last question here, if the experiment was run and 32 grams were collected, what is the percent yield? Remember that percent is actual over theoretical times 100%. The theoretical yield is always the one that we do from calculations. The actual yield is always the one that comes from experiment. So when you see the word experiment and a value attached to it, you should know that that's the actual yield. So 32.0 grams up top, 42.6 grams on the bottom times 100%. 32.0 divided by 42.6 times 100 to three significant figures, 75.1%. That would be the percent yield. Okay, we're on into chapter 9 now. Chapter 9 concerns itself with electron configurations. And for chapter 9, let me pull up here a periodic table because it's going to be hard to do this without one. All right, so here we have our periodic table. This is the same periodic table that you're going to get on the exam. And in the case of number 5, all of these that were being asked for, we're asking for the full electron configuration. So that means that we're always starting with 1s, and we're always going until we get to the very end. And notice that there are ions mixed in here with elements. So just to kind of refresh your memory here, remember we can block off the periodic table in terms of zones. So we've got the S zone, we've got the P zone, we've got the D zone here in the middle. And we have to remember the D zone is n-1. And then we've got the F zone down here at the bottom. And we got to remember that the F zone is n-2, although we've already gone through the fact that we're not going to actually use it. So in that case, it doesn't matter as much. All right, our first task is nickel. Nickel is right here. And so since it's a full configuration, we're going to be starting here at the top, and we just work our way through until we get to nickel. And nickel is in the 3D zone. So every configuration is going to be full until we get to that 3D. So we got 1s2, then 2s2, then 2p6, then 3s2, then 3p6, then 4s2, then 3D. Okay, 3D is where we're supposed to go. Now we count. 1, 2, 3, 4, 5, 6, 7, 8. 3D8. $3D8 for the nickel. Our next one is aluminum. Aluminum is right here. And so aluminum, we're looking at 3P. Its configuration ends there. And so we're going to do the same thing. 1s2, 2s2, 2p6, 3s2, 3p. And now we're at 3p. We count. Aluminum's the first one, so it's 3p1. For letter C, oh, letter C is an ion. For ions, it's a matter of moving the boxes. So in the case of a negative ion, we would move to the right. In the case of a positive ion, we would move to the left. If we have to move through the D block, we've got to remember one extra rule about energy levels. Otherwise, it kind of works out okay. So fluorine is right here. F minus would be a -1 charge, so it's going to be one more. So one more to the right would be neon. And neon's last configuration is in 2p. So it would be 1s2, 2, getting ahead of myself, 2s2, 2p, 1, 2, 3, 4, 5, 6. Because the F minus ion has 10 electrons in it and not 9. And so it's got the same configuration as neon. Neon's configuration is 1s2, 2s2, 2p6. For nitrogen, nitrogen is here. Nitride ion, N3 minus, would be 3 electrons more. 1, 2, 3. Oh, wait. It's the same as neon. So we're going to make the exact same configuration. 1s2, 2s2, 2p6. The last candidate here is oxygen. Oxygen is not an ion, it's just itself, but it also resides in the 2p block. So its configuration starts with 1s2, 2s2 as well. It ends with 2p, 1, 2, 3, 4, since it is the fourth element in that block. Okay, so that's number 5, where we had to do the full configurations. For number 6, we just need to do the noble gas configurations, which are a lot easier. So for the first one, we want to look at titanium. Titanium is right here. We want titanium 4 plus. So when we come to transition metals that are going through this, it's sometimes easier to take their configuration and kind of do something with it, figure out what electrons are going to go away. So in the case of titanium, remember, this is a noble gas configuration, so we go backwards to the nearest noble gas, so that's argon. And then its normal configuration would be argon 4s2, 3d2. But this is titanium ion, in particular titanium 4 ion. So it needs to be 4 electrons fewer. And so from that standpoint, we need to go backwards. 1, 2, 3, 4. We need to take 4 electrons away. Now, here's where it gets confusing with transition metals. With transition metals, we focus on the energy level before the order. So these 2 electrons actually get removed first. So if this was titanium 2 plus, this would be the configuration, argon 3d2. Since it's titanium 4 plus, it's actually kind of a moot point. All 4 of those electrons go away. It's just argon as the noble gas configuration. For germanium, germanium's right here. Its last configuration is going to be 4p. Since we're doing noble gas, we can go backwards. So go back to argon. So argon, and then we just fill in the rest. 4s2, 3d10, 4p, and germanium is 1, 2, the second element, so it's 4p2. For iodine, iodine is right here, but we're talking about iodide, I minus. So one more electron, that's going to move it to the configuration of xenon. If we are writing the noble gas configuration of a noble gas, all we need to do is just put that noble gas's symbol in brackets and call it a day. And so that's all that we did. Iodide is xenon. Argon is already noble gas. So we just need to put its configuration as itself. Arsenide, As -3. Okay, arsenic is right here. Arsenide would be 3 more electrons, so 3 to the right, 1, 2, 3. That puts us on krypton. Krypton's a noble gas, so we do that, and we're done. All right, for question 7. Question 7 is about Lewis structures for oxygen and ammonia. For this is a chapter 10 kind of thing. What we need to do is we need to do the Lewis dots. So for oxygen, oxygen is here in group 16. It's going to have 6 Lewis dots. Remember, for Lewis dots, we have to separate them until they have to be paired up. And so I've got 1 oxygen there. I've got another oxygen here. And I would just pair up the unpaired electrons to give me the bonding. And so that's going to give me a double bond between the 2 oxygens. And each of the oxygens is going to have 2 sets of double dots left over. Does this satisfy the octet rule? Yeah, 2, 4, 6, 8 for each oxygen. So it's playing along very nicely with the octet. For ammonia, ammonia is in group 15, so it's got 5 valence electrons. 1, 2, 3, 4, 5. Hydrogen is in group 1, so it has 1 valence electron. And since hydrogen only has the 1 valence electron, it's not going to be the atom in the middle. Remember, we always choose the one that has the most unpaired dots. For the oxygen, it didn't matter because there are only 2. But if we have a molecule that has more than 2 atoms in it, we've got to figure out what everybody's sticking to. And the atom with the most unpaired dots is the one that we stick to. So now we start pairing everybody up. And that's going to give us ammonia. So nitrogen in the middle. Single bonds to each of the hydrogens. And 2 unpaired dots left over. Nitrogen has 2, 4, 6, 8, so it satisfies the octet rule. Each hydrogen only has 2 from the bond, but that's okay because, again, remember, hydrogen and helium being in that first energy level only need 2 valence electrons to fill up that energy level. Okay, home stretch time. We've got just the chapter 13 solution stuff left. So we can say goodbye to the periodic table here because we're not going to need it. Now we're just getting into calculations related to solutions. What is the mass percent of a solution prepared by dissolving 20.5 grams of solid potassium iodide into 50.5 grams of water? So since it's mass percent, we just got to remember what the formula is. So mass percent would be mass of solute over mass of solution times 100. The solute is the Ki, so 20.5 grams. The solution is the Ki and the water. So 20.5 plus 50.5 would give us 71.0 grams of solution. Multiply that by 100. 20.5 divided by 71.0 times 100. Three significant figures would be 28.9% Ki. Right. What is the molarity of a solution prepared by dissolving 64.3 grams of magnesium nitrate into 475 milliliters of water? Okay, this is a molarity question. So for molarity, we need to remember our definition. It's moles of solute over liters of solution. So right now, we don't have either of those things. Now, it isn't going to take much to convert. So what we need to do is we need to convert this grams into moles, and we need to convert this milliliters into liters. That'll give us the moles and the liters that we need. So starting with the moles, 64.3 grams of magnesium nitrate. To turn the grams into moles, I'm going to need a molar mass. For that, I'm going to need my periodic table. Magnesium is 24.31. Nitrogen is 14.01, and there are two of them. Oxygen is 16, and there are 6 of them. 148.33 is the molar mass. Since we're only converting 2 moles, that's the only step in our calculation. 64.3 divided by 148.33 is the three significant figures, 0.433 moles of magnesium nitrate. So we've got the top part figured out now. What about the bottom part? I need to turn the milliliters into liters. For that, 475 milliliters. There are 1,000 milliliters in a liter. So this would be 0.475 liters. Point 0.433 divided by 0.475. The three significant figures would be 0.912. All right, 10 and 11, the last two questions on here. Question 10, complete the following reaction by writing the correct formulas for the products and then balance the equation. Okay, there is a question like this on the exam. It mirrors some things that we've been asking you to do in lab, as well as in different parts of the lecture. How do you do it? Easiest way to go about it, honestly, um, start by identifying your charges. You've got two ionic compounds here. You know it's double replacement. So at a bare minimum, you know that the calcium, and the copper are going to switch places. You're going to have calcium chloride as one product. You're going to have copper hydroxide as another. But I don't know if these are the correct formulas yet. And the reason I don't know those is because I don't know what the charges are. So from a charge standpoint, this is where I need to pull out my periodic table. So my periodic table says, oh, calcium's in group 2. It's a +2 charge. If it's +2 over there, it's +2 over here. Hydroxide's a polyatomic ion. If you memorized it during our look at nomenclature, you know that it's -1 in charge. But if you didn't memorize it during that time, you can still figure out that it's -1 in charge because you look at it and go, okay, hold on a second. I know that in total, it has to be -2 in charge, right? That's what charge balance is all about. I've got two of these. So if a total charge is -2 and I've got two objects, 2 divided by 2 is 1. That must mean that my hydroxide is a -1 charge. If it's -1 over here, it's -1 over here. On the flip side, copper. Copper is a transition metal. Ugh. Can't use the periodic table to predict copper's charge because transition metals have multiple charges. But I can look at the chloride and say, oh, wait a second, chloride's not a transition metal. Chloride's in group 17. Halogens always have a -1 charge. And if it's -1 over here, it's -1 over here. And since this is the formula, and I only needed one copper to balance out the chloride, the copper must be +1 as well. So now I've got all of my charges. I've got everything figured out. I just need to determine what the chemical formulas are going to be. Calcium's +2, chloride is -1. The charges do not balance. So I got a crisscross. The 2 charge becomes a subscript. The 1 charge becomes a subscript as well. Calcium chloride is CaCl2. Copper is +1, hydroxide is -1. The charges match. Don't need to do anything else. Now I know I've got the correct compounds with the correct formulas. Now I can go about balancing. From a balancing standpoint, I have 1 calcium on each side. I've got 1 copper on each side. The things that are out of balance are the chlorides and the hydroxides. I've got 2 over here. I need 2 over here, so I'm going to put a 2 there. And for the chlorides, I have 2 over here. I need 2 over here, so I need to put a 2 there. Did that balance everything else out? Well, I now have 2 coppers over here and 2 coppers over there, so it's fine. This is my balanced chemical equation, so I've done that part. If 12.5 milliliters of 0.46 molar copper 1 chloride is needed to completely react with 22.5 milliliters of calcium hydroxide, what is the solution of the calcium hydroxide? This is where we need that titration equation. M1V1 over N1 equals M2V2 over N2. I'm going to make this side the copper chloride side. I'm going to make this side the calcium hydroxide side, just so that I keep everything kind of straight and, I don't accidentally cross things over that aren't supposed to. So M1, so the molarity of the copper is 0.46. The volume was 12.5 milliliters. And remember, N comes from the balanced chemical equation. So for copper chloride, that was 2. On the other side, for the calcium hydroxide, I don't know its concentration, but I do know that it had 22.5 milliliters, and its coefficient is 1. To get M2 by itself, I need to multiply both sides by 1 over 22.5 milliliters. When I do, my full right-hand side of the equation cancels out. Milliliters cancels out here. So I've got M2 on the one side, and I've got the calculation coming here. 0.46 times 12.5 divided by 22.5 divided by 2. And to two significant figures, because there are only 2 in this original calculation, I get a 0.13 molar calcium hydroxide as my concentration there. So there you have it. That is the entire study guide from number 1 down to number 11. A couple of things to just be aware of. Some of the questions, so for example, like these electron configuration questions, I did write a few extra in there just to give you some extra practice. On the exam itself, you're not going to be asked to do this many. So if you're kind of using this as a timed test kind of dry run, just do keep that in mind, that if you were really bogged down in this section, you don't have to do as many of them as all of that. But everything else was pretty true to form. So if you have any questions, if things come up that you're unsure of, please do feel free to reach out to me over this weekend as we get ready for test day next Wednesday, and get ready to take care of this exam and hopefully show that we have made some real strides here in the past couple of weeks and have improved considerably, especially coming off of where we were at spring break and at midterm time. So with all that being said, have a great day, and I will see you in class.